This is a continuation of the topic about flow impact and fluidized beds. In the previous lecture, I talked about flow impact beds and I discussed the different equations that can be used to calculate the pressure drop if we have laminar flow or if we have turbulent flow. And the main issue was, or the main equation was the Ergun equation, which can be used for all, let us say, regions of the flow, regardless of its type, if it was laminar or turbulent or transitional flow. And we solved two examples to show you how to use the Ergun equation by its two forms, which are the regular one with the dimensions and the non-dimensional form. From now on, I'm going to talk about fluidized beds. So what do we mean by fluidization? So now I'm talking about something called fluidized bed. So what do we mean by fluidization? So fluidization is a process in which the solids are caused to behave like a fluid. So because now the solids, the particles which are inside the packed bed, they start to move as a fluid. So we call this process fluidization because the solids are behaving as a fluid. So by blowing gas or liquid upwards through the solid filled reactor. So I have, this is the reactor, let us say, and I have this support here mesh, and this is filled of particles. As we said before, I am blowing gas or air, and those particles now, which were in the first, let us say, the packed bed, they are staying in their place. But now I'm going to increase, let us say, the velocity or the flow rate of the air going through the particles, where they will start to move and they will behave as a fluid. This is why this process is called fluidization. So let me go through this slide with you, like statement by statement. So when a fluid flows upward through a packed bed of particles at low velocities, the particles remain stationary. So I have this. Again, this is my packed bed, this is the support, and you know the holes, I have the holes, and the fluid goes through the, let us say, those are the particles here. So at low velocities, the fluid is just passing through the particles, and the particles remain stationary. So the particles will just remain where they are. So as the fluid velocity is increased, as I just increase the velocity here more and more, what will happen? The drag on the particles increases, and there is a point reached where the pressure drop balances the effective weight across the sectional area. What does this say is the following. So I am increasing, let us say, the flow rate here, the velocity of the fluid, and the particles are staying where they are, but then I will reach a point where the drag force, let us say, balances the weight. So the forces on the particles will balance. So now they will be hanging there. A small increase in the flow rate causes a slight expansion of the bed from its static packed state. So as I increase it even more, I will start, if this was the original volume, now they will expand. The particles will just go up a little bit and the bed will expand. So unless a small increase in the flow rate causes a slight expansion of the bed from its static packed state. So I don't have the static packed state. I'm going to the, let us say, the fluidized state, where the particles now are moving. They are not stationary. So further increase in the flow rate allows the bed to expand even more, and the particles become free to move around, and the bed is said to be fluidized. So now if I increase it even more, now the particles will be free from each other and they can even move freely. Okay, they can move freely. They are not intact with each other particle, and in this case the bed is said to be fluidized. So the state when the bed just becomes fluidized is known as the minimum fluidization state. And this is important. Actually, all of the calculations that we are going to do at the end is to calculate when the bed will reach this let us say, situation of the minimum fluidization. So we want to know what is, for example, V prime MF, which is the minimum fluidization velocity based on the empty tower. You remember from the previous lectures about the back beds, when I have V prime, this was the superficial velocity of the back bed, but now I will just put this MF. So I'm talking about like the superficial velocity at minimum fluidization. يعني هذه السرعة اللي أحتاجها لما تصير عندي الفلويدization. The same thing, epsilon E or epsilon F is the minimum fluidization porosity. Porosity is the same as void fraction. So this is the minimum fluidization porosity. This is the porosity that at which the fluidization will take place. And L طبعا is the length of the backed bed in the past. And now when I have this MF, then I'm talking about the minimum height of the bed at the onset of fluidization. So at the onset of fluidization, لما تبتدي عندي fluidization, this will be the length of the fluidized bed. So what are the types of fluidization? We have three main types. So on increasing the velocity, three types of fluidization may occur. So the first type is called particulate fluidization, and here, which is this is the fixed bed, this is the packed bed. This is the first type, which is the particulate fluidization. So the bed simply expands and remains fairly homogeneous. So this is like at this stage I have the fluidization, the onset of fluidization at the particulate regime. But what will happen if I increase even the velocity more? So I will go from the first stage, which is the particulate stage, into the bubbling regime. So what's the bubbling regime or the bubbling fluidization? So at higher velocities in the gas solid system, gas voids containing a few particles form and pass through the bed. As you can see, now I have those bubbles. So here I don't have bubbles in the particulate regime. So the bed is still homogeneous, no bubbles. But at the bubbling regime, I will start to get those bubbles. And only a small percentage of the gas passes in the spaces between the individual particles. So now I don't have gas going here. All the gas is going through bubbles. And it's going here as bubbles and just going up the bed. So this is called the bubbling fluidization. What if I increase the velocity or the flow rate even more? I will reach this stage. It is called slugging. So as you can see, this is the slug flow regime. Here the bubbles tend to collapse and they grow as they rise in the bed. So they collapse and they grow as they rise in the bed. If the column is small in diameter with deep bed, bubbles can become large and fill the entire cross section of the bed. As you can see here, bubbles will just collapse and reform, and they can even fill the entire diameter of the bed, which is called slug flow regime. So I have the fixed bed, I have the particulate regime, which is at which the onset of the fluidization will happen. Then if I increase the velocity more, I will get the bubbling regime, وبعدين I am reaching the slug flow regime, slugging. This is this image just to show you again the different stages. So the fixed bed, and now I have the minimum fluidization at the particulate regime. I increase the velocity more, I'm going to the bubbling regime. بعدين increase it more, I can have the slugging. As you can see, the bubbles, they are just covering the whole diameter. Then I increase it more, I can reach something called turbulent bed. It's like boiling. The fluid will be similar to as it boils. And finally, if I increase the velocity even more, I will have this called pneumatic transport. So I am transporting the particles. If they are not, let us say, if I'm not keeping them here by any means, they are just going to go out of the bed. This is why it is called pneumatic transport. Pneumatic means I'm using pressure to transport fluids from one place to the other place. So where do we apply fluidization? So fluidization is widely used in commercial operations. The applications can be roughly divided into two categories. There are a lot of applications, but we can have physical operations such as transportation. As I have just said, in the pneumatic transport, I can apply high pressure, where the particulates will transport from one place to the other. I can heat them, I can mix the fine powder, etc. All of those are physical operations. I don't have any chemical reactions. Or I can apply fluidization in chemical operations, such as reactions of gases on solid catalysts. So if I want to have this reaction, then I can have good mixing when the particles move with the fluid going between them. So this can be considered as a chemical operation in fluidized beds. So what I have done here, I just introduce you to fluidization. So we said fluidization is the process where the particles are going to move in the backed bed and they will behave as a fluid upon increasing the velocity, which is upon increasing the velocity above the, let us say, the minimum fluidization velocity. We said we have different types of fluidization. We have the particulate fluidization, where the bed is still homogeneous. Then if I increase the velocity even more, I will start to have the, let us say, the bubbling or fluidization, then slugging, and upon increasing it more, I will have a lot of turbulence, and finally, if I increase it more, I will have the pneumatic transport. So this is an introduction to fluidization, and in the next lecture, we'll start to introduce you to the equation that can be used to calculate the important variables in the fluidization problem.